Hi, my name is Andrew McLaren. Today we're going to be going over a very difficult physics problem around rotational inertia, forces, and torque. It is a doozy. We're going to be talking about my technique, which really relies a lot on reference frames and signs versus the other common ways people usually do these problems with some kind of shortcuts or assumptions. And then we'll do a preview of this problem worked out so you can kind of see the general idea and then actually go through it step by step doing the math and talking through each step throughout the while. It's going to take a long time to do this problem. Um, they're kind of complicated to wrap your brain around. Math isn't so bad, but it's kind of hard to figure out what's what. So the main thing here is that you want to know which way this is going to spin. Like that's the main idea on this. And so we're considering the torque of these two, and I know one of them's bigger than the other. Like I know B is heavier. And because it's heavier, I know it's going to spin this way. Spins slash accelerates this way. And so it's a matter of like trying to figure out how the torques combine and the signs of those torques combine. And it gets a little bit confusing because there's G and there's mg. It's like, are you adding mg? Are you subtracting mg? And it's really, really messy. So I'm going to help you with getting your bearings with our concept maps and our reference frames and our all of that stuff laid out. And that's the big picture on what I'm going to try and do in this problem. Um, there's a number of videos that you may have seen online. I'm just going to show you one. I don't really like them though. You'll see why. So this is a really good worked example of how people will oftentimes do these problems, and I've got a huge issue with how they've written the torques. You're subtracting torque 2, but it's very unclear as to why. Um, for me, I think that the sum of torque is what he's got right here is equal to the I times the A. So this is really the sum of the torques. And the traditional way of doing this is that you subtract things um, that are going to be negative. But then it's like, hold on, don't subtract T2 that's negative because now you're adding it, right? So you need to make sure that T2 is, in this context with how he's doing this, T2 should be a positive value that gets subtracted. So you're going to have to like minus the M2G and the M2A if you were to set up this giant equation, like the minus M2G and the M2A right there. So there's ways to think through this, but I really don't like how they've related T1 and T2, and it's just like subtract the MA and add the MA here, and it's like, wait, hold on, what's going on? And it can get a little bit weird. So I'm going to show you how I think through this problem in a slightly different way that actually makes sense with our coordinate system because he's just switching what is positive and negative depending on the context without explaining it. So I'm going to go a little bit slower and more in depth to help you wrap your brain around that. So I've already done the work. I'm going to go through it and just generally explain it. And then the next section, I'll actually go through solving each number so you know what it looks like to go through it that way. If you want to skip this part and go through it there, that'd be fine. That would allow you to kind of pause and check. This is going to be a little bit more direct. It's still going to take a long time though. So when we're looking at this problem, the main thing is defining that direction and knowing that the positive acceleration for A is going to be going up, the positive acceleration for B will be going down, right? And it looks like this will be spinning that way. And so I was thinking about considering that positive spinning that way. In the end, it didn't work out, but I was like, hey, maybe that is the positive spin direction. Let's think about it if that were the case. So you can do your sum of forces here. And this is a little bit more typical with your positive being up and your negative being down. This, you'll see that we do want to flip these signs in a little bit. But then you've got this sum of forces, which is positive going down, and you got the sum of forces being positive going up here. So the acceleration, this tangential acceleration, should be like a positive value for going down for B. So that's going to be relevant in this problem. That's kind of why the signs are a little bit different for A and B, is because we're considering one of the torques to be positive and the other one to be like a negative number in our reference frame. So we do need to kind of flip signs for B. That's the main idea here. Then if you wanted to like rearrange and plug in some numbers here, knowing that these should be positives and negatives, you can set up something kind of like this. And I know that f of t itself should be positive and it's going to be equal to that. Now I had to, it was a negative 19, but it got brought over. Like you see the negative 19 there, but it got brought over to the other side, so now it's being added. And vice versa, if we're looking at b here, you end up getting this negative as opposed to this positive. So it's a little bit different because the f of g's were different signs that you brought over to the other side. Now both accelerations were positive, so their sum of forces both should have been positive. That's why it's like the 3 and the 2. So very, very similar in that regard. And then what we can then do is, I was also trying to think about like what's going on with my numbers here. If I wanted to flip the signs, that would be kind of what's going on, but that's not what we want to do, that little red. It's just kind of like a side thought. What if we did that? So then I was thinking like, okay, what's going on with this angular acceleration? I could consider that positive spin going the way that's kind of different than normal, but then it's kind of like this force is applying positive torque, although it normally applies negative torque. So that's kind of an issue for us. And you can imagine like the rope's pulling down on the pulley at these two sides. This is the pulley and the rope is pulling down on both these sides. So it's totally acceptable for these to be going downward and then the tension to be going upward here. It just depends on our reference frame and what positive negative means at that moment for those forces and that acceleration. So if we look then back to like the normal way of thinking about this, normally spinning that way, going clockwise, that would be negative, and going counterclockwise would be positive torque or positive angular acceleration, which kind of works out nicely because if we've got ft here, that means it's kind of applying a positive torque because it'll get it spinning that way. That's basically how I think about that. But you can also think about like a negative radius and a negative force is a positive torque. This is a positive radius and a negative force, so that's negative torque. So the B should be creating negative torque and A should be creating positive torque. That ends up having an angular acceleration that's negative. So we then have this one equation where it's like, okay, I know the angular acceleration was going to be negative, so this total torque should also be a negative value. But the torque from A was positive and torque from B was negative. In that video, he had done this as like TA minus TB. I wanted to have TB just be a negative number. It just makes more sense to me keeping the reference frame consistent like that. And then I got the I value, which was just a pretty simple calculation. So we have these expressions for what the torque of A and the torque of B were. So we were able to just times those by the radius to get, or sorry, the tension times the radius would give you the torque. So we've just kind of plugged those in there. And then plug them back in here. So it's like, okay, if you times whatever that was for that torque, that expression that I had written earlier, this number times 0.2, that would give you the torque. And so we can just kind of plug that in where the torque was in this expression. And you can kind of see these positive and negative pieces and how they're kind of coming in here. And I know that this total thing should have a negative value and this total thing should have a positive value, which is like what I've done with these brackets, just to kind of give myself some reference frames. And so I've got this negative spin, and I should be able to just kind of plug in everything at this point because I have everything besides that angular acceleration. And it's a little bit messy with the math, but you can kind of see and follow along where we're combining like terms. We're getting those ATs that we end up combining and the newtons, which we end up combining, so on and so forth. It's a little bit nasty math here, but I think that this is better and it makes more sense to me than just a saying like, oh, this is going to be a positive value that you're subtracting. That was just kind of weird to me with how most people will do this type of problem. And you end up getting for this, I think it's 8.17. Interestingly enough, you can kind of go backwards and kind of plug it back in and see like, oh yeah, this torque, yeah, that is negative, right? And so on and so forth. I think for this problem, I solved for it as a positive value by setting this whole thing equal to negative. Yeah, I think I'd written this as gray, saying that this whole thing was negative, but then I switched to black, making that a positive number, and this whole thing a negative. And so I was able to then just get like the acceleration as a positive value just because I kind of flipped my reference frame from this gray reference frame back to this black. Yeah. It is a lot. This problem is insane. And that's kind of my thought process on how to go through it. And then we'll actually do the numbers next. Okay. Yeah. All right, so let's say we're starting this problem from scratch. Kind of like what we said in the very first part of the video is that we want to be careful about signs. And so one important aspect of this is that we're going to have an issue if we say the acceleration of b is negative here. It causes us to have different acceleration like signs, which we don't want. It just complicates the problem. So if we're looking at like part A right here, we've got the sum of forces for part A, and it looks to me like it's got this force tension and the force of gravity. So if we're kind of just doing this box right here, there's this force of gravity, and then there's some sort of force tension. We know it's accelerating up, so this force tension is bigger than the force of gravity. So we've got some sort of sum of force that's going up in the positive direction, kind of like this. That's going in the negative. And very similar to that, we've got B over here where we've got our force of gravity of B. We've got this force tension of B. And the force of gravity is winning because we're seeing an acceleration that's going downwards. We'd said that it should be spinning that way. So that works out like that. And then we've got this sum of forces as well, which should be negative. If you were to, have this number and subtract it from it, it should give you this. So we could have this be negative and that be negative and that be positive. Or we could switch the signs and consider when this is negative, this is positive, and this is positive. So you can switch the signs. That's totally fine. And then your forces actually work out pretty nicely. You just got to be careful. And this is also part of the reason why tension I write as F of t is that just is a little bit clearer that it's not torque that we're talking about right there. And we should always do subscripts that clearly designate what we're talking about here. So we've got like A and B. So I'm just trying to wrap my brain around what the signs of these would be, because there would be like an M times an A, and then this, I think that's just going to be the FTA, which has a positive value. And then we're going to be adding to that this should have a negative value, so it's going to be the M times the 9.8 meters per second squared. But I believe we have the mass of A, which was 2, I want to say. Yeah, it was 2 kilograms. So we can plug that in here. So we've got this positive value here for the M times A. And this thing should all be a negative, so I would just do a negative 9.8 times the 2. It doesn't really matter which one's negative because the whole thing ends up having a negative value. So we've got the FTA, and then minus, that's going to be 19.6 newtons. And so given that this is a positive and that this whole thing is a positive, which is a pretty big assumption that we're making, everything falls apart if that's not true. Then this FTA is equal to that positive value minus 19.6 newtons. And if you conceptually go back to this problem, it kind of makes sense. Like, oh yeah, you're gonna have to take that off of this number to get the other one. Yeah, so that's kind of one way of thinking about it. It's like, oh, okay, you gotta kind of see the difference there, and the difference between these two is the f of g. And vice versa, you can do the same sort of thing here, where we've got m times a, but this is now for b, and the whole thing needs to be positive. So that's why we're lining it up with this reference frame where we've got a positive here, a negative there, and a positive there. Because if we use a different acceleration, things are going to get messy pretty quickly in terms of the work later on when we plug in the m times a. We want to have the same acceleration value, essentially. You don't want like a -3 and a +3 because then they cancel out instead of adding up, right? So we've got this right there, and then we've got this FTB, which the whole value of that should be negative. And we've got the FGB, which I believe was the mass of B times acceleration of gravity. But that's going to be a positive value. Yeah. This whole thing is just going to be the m times b times g, but it has a positive value there. And that was that 9.8. And this was the 3 kilograms for the weight of B. So B is weighing a little bit more than A. Hence that that slight difference there. So we got our slightly different but very similar numbers there. I'm just double checking what we had on the other one. Yeah, this is 29.4, which is a positive value. And so you're gonna have to end up subtracting that from the MB times A to get the FTB, which we should have as a negative value because it's going to be spinning the thing in the negative torque direction. So we want that to be a negative value. I mean, it still is. So we got the M times V times A plus the 29.4 newtons, because that should be newtons. We do have the MA and the MB. We could plug those in here. That would totally be fine. So why don't we do that? It's going to be 2 kilograms times A, the acceleration of A, minus 6 newtons. And then very similar to this, we're going to have, I think this was the 3 kilograms for B times acceleration of B. So we can kind of see here that that's similar, but slightly different. In terms of their format, one's being subtracted, one's being added. So then that's looking pretty good. I'm pretty happy with that. But then it's like, okay, we've got our torque. This is our torque total, which is equal to the torque of A plus that torque of B. And let's just keep the colors consistent, seeing how we've been using these two colors for these two. And we know that this thing, these should have opposite signs, these two torques. One's going to spin positive, the other one's going to spin negative. Now, I'm just kind of knowing this problem myself, and that we've got like these two different torques that are pulling down. We've got the TB and the TA here. And then we're spinning, and so it's, I think we have the acceleration is going this way. So we could consider that to be a negative direction, or a positive direction. So I think that we could consider that positive here, and if that was the case, this would be positive, that would be negative. So it's actually the opposite. It's the standard way that we're looking at this problem, where this is going to be a negative value. And this is a positive, and that's going to be a negative value. Going with the convention of a positive radius and a negative force give you a negative torque. And then if you have, because it's like that to that, or if you were to go from a negative radius and then a negative force, your torque ends up being positive. So that's kind of what we've got here. We've got a negative force and a negative R. So the TA should be positive and the TB should be negative. So we kind of know the signs of these things at this point and what they should be. And then it's just a matter of substituting some stuff in. So we've got the torque of any torque could be considered the force times that radius times the sine cosine. But because these are at a 90-degree angle, you could kind of drop that. Because that whole thing, that has a value of 1. We can see the torques are 90 degrees from a radius in this context of this problem. Like there, you got your radius going from here to there, and then it's 90 degrees to go down to A. So we've got like the torque is equal to the force times that radius. So we can say that a little bit more generically, we can have this is going to be equal to the tension of A, and that's going to then be times R, and same for that of B. You could just copy the whole thing and just replace that with B. And we're getting close, but now we can, I think what we have is we then substitute, yeah, because we have the f of t here and it was a positive value right there. So that sine-wise should be working out for our problem. So we've got that is going to be then multiplied by the radius, would give you the tension or the torque of A, because that's the force and that's the respective radius. I believe the radius was they gave us was 0.2 in this problem. I'm pretty sure, just because I've seen this problem a fair amount. Yeah, the radius is 0.2. And so we've got that tension now. Looks pretty good. We need to do the same thing for this tension of B though. So I'm just gonna grab that for B. And we need to double check our signs just to make sure that everything that we're doing with our signs is working out correctly. Like it's giving us torques that are appropriate values. Yeah, let's put meters on that as well. So I'm just looking at this. I know that this whole thing's value and this whole thing's value should be negative. So I'm just double checking that. Yep, FTB should be negative. Like this thing is negative and this thing's whole value is negative. So that does look like that's done correctly. And that means that this is positive and this was the positive value times that. So now we just take that and I'm going to rewrite this formula and just bring it down. Because now we've got our first part plus the second part, right? And it's just a matter of doing some multiplications. We're actually going to go through those multiplications. And then also there was the tension total is equal to I times A. That's just one of your formulas that you have. Like I is that moment of inertia, I believe, and this is your angular acceleration. And so I believe we have values for that as well. Now I for a disk is equal to 1/2 mr squared. And so we can just plug in that. Now we have the mass of, this is, you gotta be careful, this is the mass of the disk, right? Not of A or B. But the disk, I believe, was just 2 kilograms. They made it easy for us. Yeah, they're nice to us. So we've got our 2 kilograms, that mass of the disk, times the radius, which was 0.2 squared, 1/2. And 1/2 times 2 is cancel out, so it's basically just 0.4 squared. So it's 0.04 For the angular momentum, this would be, I think it's kilograms meters squared. So we've got an I value there. So we've got basically everything here besides this angular acceleration. We should be able to just kind of plug it in and have it work out. So we've got 0.04 kilogram meters squared times that angular acceleration. And then we've got, looks like this is going to get distributed the 0.2. So we need to multiply it to both of those things, and same here. And so we've got the 2 times 2 kilograms times 0.2 meters times the acceleration of A minus 19.6 newtons times that 0.2. And then that's going to be that first part, and that we should be able to say that that would work out to being a, I think it's the positive value. And then we're going to do this, the second piece. 3 kilograms times the 0.2 meters times acceleration of B. That's all that first part, I believe, and then plus the 29.4 newtons times 0.2 meters. That whole thing, that should have like a negative value basically. So I've got 2 times 0.2, so that's 0.4 times the acceleration A. And then what is that? 19.6. I'm gonna need my calculator for that one. Or I could check my previous work. But we got 19.6 times 0.2. Let's see. Yeah, it's 3.92. And that's Newton meters. And then we gotta be careful here. This is where things get a little dicey in terms of summing things up. Now, if you've been paying attention, you'll realize that I did something wrong quite a bit ago, but it doesn't throw things off that much. We just kind of need to change some signs. Now, the reason that I knew that this was wrong was because this should be coming out as a positive thing. But this is negative, and that this is supposed to be coming out as negative, though this part is positive. And we had said that accelerations should be positive. So something's really kind of strange. And I was looking back at this and I realized I'd actually messed up some of these signs. So if we go back here, way long time ago, we had rearranged going from here to there. And I somehow messed that up. It should be minus 29.4. This was a positive value here, but we're subtracting it on the other side. So you're subtracting the 29.4 newtons from both sides, leaving you with that negative 29.4, not positive. It should be a negative for the second number, which means we also need to flip our signs on this guy. So this one's should now be a positive 19.6. So those guys were kind of flipped, but I forgot to bring it over correctly. Somehow silly mistakes like that do happen. So just be careful. And then as you're going through the problem, you'll recognize, actually, you may have recognized it earlier. Wait, if I've got a positive number here and a negative, that kind of worked out. But here is like you're combining a positive with another positive, get a negative, which just does not make sense. So that was kind of an issue. And you would also see like mathematically that it wouldn't work out if you're trying to go through these steps. I just kind of saw that at this point because I was like, hold on, that's not going to be negative as is. So I believe that this needed to be a positive value and that this needed to be a negative. But don't just flip signs. Try and make sure you understand why or how those are a little bit different. It's because of those different reference frames. But now we do have something that looks a little bit more like my other notes that I've done on this problem, and we should be able to solve for it. So we've got like the what's this? 0.6 times AB minus the, what is it, 5.88 Newton meters. And then you just combine like terms. So we've got the 0.6 and the 0.4. So you got like 1 AT, because what we can say is AA is equal to AB, which is that tangential acceleration. So we've got that tangential acceleration, AT, and it's one of those times AT. And then we've got a minus, because if you end up, this should be a positive because it was that positive up above. I forgot to flip that sign from when we did change that with the purple. So now we've got, I think this is 1.96 Newton meters. And that is equal to a negative angular acceleration. So it's spinning in the negative direction. So this whole thing should have a negative value. So it's a negative. So you could do I times A and have the whole thing have a value that's negative, or you could set this as positive and bring the negative out front. Either or is fine. But I like to set this as like a positive number and then just have a negative out front. So we've got negative I times the angular acceleration is equal to this guy right here. And then we need to substitute, and we're super, super close. We can say that we've got the angular acceleration times the radius is going to be the acceleration tangent, which kind of makes sense because it's radians per second squared, and now it's being multiplied by some meters, so now it's going to end up giving you like meters per second squared. So that is kind of unit wise how I think of that. And so now we can say we've got that AT, and we're going to substitute the angular acceleration times the radius, which was 0.2. So now you've got 0.2 times 1. So there's a bunch of units here, but it ends up being 0.2 times the angular acceleration minus 1.96 Newton meters. And then this was a negative, like the whole thing is a negative value. And we got the I value, I believe, earlier. Yeah, we found the I value to be 0.04. Whatever with the units, honestly, at this point. And then we've got our angular acceleration. So you bring that over, you've got negative, I think it's 0.24 times that angular acceleration is equal to that 1.96 Newton meters. You divide both sides by that, and you should get your angular acceleration of, well, this is that negative as well. Yeah, of that 8.17. So be careful with those signs. Even I, knowing this problem, going through this experience with it, messed that up. That's probably gonna be where most people mess it up. Thank you for joining me. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wisant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wisant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.